Welcome, everyone. Welcome, Michel. We're looking forward to an excellent presentation in the CVAS lecture series, where we've now arrived at excellent presentations on shorter timescales at the centennial timescale, which will be presented by Michel Crucifix from the University, no, English and French going together. Université
UC Louvain is fair.
Catholique. And we're very much looking forward to your presentation, Michel.
Hi. Um, Thanks. Yeah, well, I didn't write the university name. I have to do that. We have to be brand friendly. So yes, I'm coming from UC Louvain. We're a little bit ashamed nowadays to say it's Catholic. It used to be indeed founded 575 years ago, and Europe was very different at the time. But we teach biological evolution, and that's not a problem. Thank you, Kira. Thank you, and welcome to everyone. This is well, Kira has put a little bit of pressure, to be honest, by saying that it will be a good presentation because I'm not an expert on centennial variability. But I started to look at it more or less seriously when I studied glacial interglacial cycles, which are the long time scales. And the point is that whichever climate record you look at, it looks noisy. And when we study these long climatic cycles, we tend to focus on the slow drivers. But all this noise, which in fact at the paleoclimate timescale is maybe millennial or centennial or maybe decadal variability, can actually matter. And it's how I started to be a little bit interested in this. And this interest was boosted or let's say structured within the page's CVAS group, Centennial Variability Across Scales. And some of this presentation will be inspired by what I've learned within CVAS. So really take it as an outsider look. What I learned myself about centennial variability and what I want to share with you. So back in the 90s, it was common if you open a textbook to see pictures like this one, and you could get pictures like this one, whether you're interested in paleoclimates or whether you're interested in weather, synoptic weather. And so the idea is the following. This is a, let's say, artistic view, or at least schematic view, of spectral power density. So let's say energy across scales with the idea that you're actually doing a Fourier transform. And it's customary to see that you have different regimes of variability. At least that was the picture which was conveyed in textbooks at the time. With the following idea, you have weather and climate, and these are two different things, two different modes of motion, if you want. Weather is something that happens, so this is period expressed in thousands of years. There will be a bit of different scales around here, but basically here we are looking at weeks, and here you are looking at thousands of, or hundreds of thousands of years even. And then in between you have a boring zone, which is called a variability gap, and which is centered more or less around 100 years. And it's a very convenient hypothesis to make because it tells you, oh, well, we have a time scale separation. We can study weather, we can study climate change, and these are two very different things. This picture evolved, and very quickly, in fact, when people started to do real spectral analysis of climate records, and one which seems to endure a little bit the test of time, which at least is displayed often, is the spectrum published by Harris and Curie. Again, there are many others, but I mean, I sort of like this one because it's both busy and beautiful. But what you have is, again, let's say here he calls it energy, but basically it's a power spectral density. Frequency, and here it's cycles per thousand of years. So I agree the scales are a little bit difficult to go through, but basically what you have is the yearly time scale, the centennial time scale, and the millennial, and let's call them Milankovitch timescales. So this was obtained, let's call it with real data. So it's really a power spectrum density estimation. I will come a little bit later on what estimating means, and it's really the statistician's job. But again, what you have is, let's call it a weather regime, a centennial regime, and then, well, what Salzman would have called a climate change regime. So here you don't have a gap, but you would still have a centennial regime where basically the spectrum is more flat. So I realized that whether there are spectral breaks or not is something which is a little bit debated in the paleoclimate community. I think we have Tina Nielsen listening to this presentation, and the Tromsø group has made some work about asking in a statistical fashion whether there is actually a spectral break or not. Today I will start from the hypothesis that there is such a spectral break. But I agree that this is open to questioning. It also depends very much on the kind of data you analyze. Here you already see a difference between the tropical and the high latitudes, and also the nature of the variable that you analyze. So what does it mean? We have to interpret this slope, we have to interpret this change in spectral break, and then we have to ask whether we have to spend time and attention on all these wiggles. Do they matter? So what are the mechanisms, and what kind of information can we instruct in this range? So this is the kind of challenge that comes up when you want to study centennial variability. So I told you about the CVAS centennial variability across scale group. There was also a special issue published in PastGlobalChanges, which I was happy to lead with Anne de Vernal and Christian Franzke and Lucien von Günten at Pages. And we asked a couple of colleagues to express a little bit their views about centennial to million variability. And in the meantime, I spent some time in the past few weeks really browsing the literature, looking at what are the recent records. And one picture that emerges is that centennial variability is very hard to document. I just show you one of the figures which was published by Anne de Vernal in that Pages issue. And what you see are different records, which are in this case estimates of sea ice. There are other records published in that newsletter, and again the literature is full of such records, but I would say the subjective impression that comes out when you look at this is that, first, if you want to study centennial variability, it's a good idea to have a reasonably long record that spans many centuries, and the typical zone where you would do that is the Holocene. That's the last 9,000 to 10,000 years, because it's where we have the highest resolution. And these records, you see different expressions of sea ice in different areas. It's a huge amount of work, of analytical work, to get these records. You get this impression that you need, indeed, you have many wiggles, you have regime changes. There is a lot of information, but which is very hard to decipher. You don't have, for example, a 200-year cycle that pops up. Like when you do paleoclimate, you see 40,000 years, like the obliquity cycles. It's very bluffant. It's hard to say here that you have something bluffant. You have regime changes, you try to identify events, and it's tedious work. So I was part of a project completely separate to CVAS, but which was also tackling this problem of centennial variability. The project was called HOPES. It was funded by the Belgian National Fund of Scientific Research. And it was based on data sampled in Belgium, and in this case, a speleothem. So for those of you who work with speleothem, know it's a hard proxy to work with to start with, because what actually generates what you will measure here, these are basically trace elements, because it was the specialty of the lab in Liège University that I was working with. Again, you have a little bit this impression that many things happen, but it's hard to really spot a cycle. But clearly you have, let's say, intermittent events. Some of them may be climatic, maybe others are not. And one of the purpose of the author of that study, and I will show a paper that the project published, but I was not co-author of that one. So see, can we understand this variability? Can we attribute it to something very clear? And you go through the usual business. You have control points like radiocarbon. You give an age scale expressed in years before present, and then you look at the literature, and typically people will try to compare with elements of explanation, and in this case it's a record of Solansky giving the sunspot number. So I guess the agenda was to see whether there was a connection between these events and solar variability. And I'm going through that paper here because it goes through a process which I think is pretty common in the paleoclimate literature. At least it seems to me that I've seen this process quite a couple of times, and I would like to, how to say, to consider it a bit seriously. The process is the following. People take this data and they do a spectrum analysis. Again, with the idea that you decompose a signal as a kind of, in this case, amplitude or period over time. In this case, the spectral analysis is using a wavelet transform. I will go a little bit into the details later. And then you see different peaks, and you want to say these are maybe significant, at least above a certain confidence level. And then you do this matching, and maybe you have an attribution. I'm going a little bit fast over this graphic because it's not my work. I mean, it's not my analytical work, and I don't want to go into all the details. What I want you to retain at this point is I would say the scientific process. And what you see quite often, at least what it seems me to have seen on many posters in conferences, is this continuous wavelet transform, where basically you take the signal and you go to this process, which basically convolutes a wavelet at different scale, and you can identify maybe periods or scales at certain, well, a signal at certain periods over certain intervals. And again, you may be tempted to do the matching. Right. Maybe one message of my talk is, tools. It's like a kit, a chef knife. You can do wonderful food with it, but you can also cut your fingers. And I think there is a danger here, and I would like to draw your attention on it. So what we need is to take really the minimum, simplest possible model that we could work with to have an idea of this spectral change in slope. And again, Tina, who is listening to us today, will recognize familiar stuff. So imagine that you have basically a two-box ocean model, a surface ocean and a deep ocean, which is forced by the atmosphere. And these are the equations that go with. I don't want to swamp you with the equations, but what you have to see is that all the terms are linear. So basically what you have is the ocean that relaxes to, in this case, the surface which relaxes to basically zero. So the temperature zero would be a reference. We are doing simple stuff. And then an element of exchange. And I realize that there is a wrong sign. It's a plus sign. I have to change that in my final presentation. But the calculations use the plus sign between the two boxes. For the forcing, well, it's something common to use noise. Let's say the atmosphere is oscillating very quickly with noise, and then you get these two equations. The equations are so simple that you can do everything analytical, and you can get the spectrum just on paper. I have to warn you, it take me a couple of hours though, because it's very simple, but you have to deal with these two equations. But nevertheless, is it what you have? So let's focus on the x variable, the fast variable first, and this is the spectral power density as a function of frequency, and I've put the parameters such that it works right. So what you have, that's the blue. You have, let's say, the weather regime. It's when x responses to f. And then you have this plateau in a kind of gap band, or I mean no man's land. And then you have the time scale of y, which kicks in and produces this secondary slope. If you just focus on y, you just have the slow time scale which kicks in at the millennial time scale in this case. Perhaps very counterintuitive, I have to say, that if you start to mix up x and y, you can really produce a very spectacular, very dramatic shape here. So basically, the mean slope will actually depend on how you have mixed x and y. The reason for it, I had to scratch my head a little bit. In fact, it was not entirely obvious to me. But basically, when you look at x alone, basically what you're doing is to track y. And so these two variables tend to fit together very well. When you start to mix them up, you start to look at another actually variable, which is the amount of energy being exchanged between the two boxes. And it's how you can have some dramatic shapes. So what you can show, and again, the Tromsø group has been active in putting that on paper, but I think it was already known a little bit before, is that if you start to multiply the number of boxes, you will actually multiply the number of breaks, and you can even come up to a situation where the slope will be constant. And actually, there are also calculations where you basically take a continuous medium, but with a diffusion, then you will have a mean slope 1 all across the spectrum. So basically, if you wanted to be very parsimonious, well, we have a model for our spectrum. It's not a very physically realistic, because basically we estimate that the whole thing here is passive and it's just forced by the fast variability. So let's play a little bit with it. So the first thing you have to know, I'm sure many of you know, but some of you don't. At least I didn't 5 years ago. So I have to tell you something important, is that this is the spectrum that you compute on a sheet of paper without doing a single numerical simulation. But what you actually observe is a realization of the process. At least if you believe that climate has that process, you observe it once. And what you can only do is to apply some algorithm, which are called by statistician estimators, and which will provide you an estimate of the spectrum. So one very tempting to use is the periodogram, which basically is doing a discrete Fourier transform and taking the square of it. It's not such a good algorithm because it has a very high variance. I will show you another one, which is more popular. It's the Weldon and Percival Multitaper method, which is inspired from Thomson. And what basically does it's so we have one simulation here of 16,000 years, and the Multitaper basically does different chunks of it with a certain window and average the spectrum. And here is what you have. So the blue is one simulation. So that's a spectrum that people might publish based on their records, assuming that have a year resolution. And the various color bands are the percentiles, 5, 50, and 95th, across, let's say, 1,000 realization. So of course, in paleoclimate, you don't have 1,000 realization. You can just take realization of your model and do 10,000 realizations of your model, or maybe compute things analytically. Here I was very privileged because I did both the data and I know the process. So basically these bands are perfect. And even though they are perfect, you already see that some peaks pop up and well, yeah, oh yeah, look at that. I have a cycle at 300 years. Well, of course, no, just a statistical fluctuation. So I think I'm telling something which is completely obvious, but maybe sometimes forget a little bit about that. But in practice, you don't even know the process. So for example, in this case, I did the same kind of simulation, but rather than using for here a random distributed forcing with a normal distribution, I use an alpha stable, which has a distribution as a power law. And then you immediately see already that the bands are very different. So even though this one seems to be large, maybe actually it's even not significant at all. So it's really not significant in this case, but maybe even with another reference model, the the confidence intervals would still be much larger yet. So nothing new under the sea, but I think we need to be aware of these things. So now, if you do a wavelet analysis, there are two ways to do wavelet analysis. One is to show a scalogram, which was shown by our friends in this case. The other thing is that you can average the scales through all the times as a frequent, you can average the power at all times as a function of a scale. And this is what you get in this case. So it is exactly the same simulation, exactly the same simulation. And here is what you get for a single simulation and the confidence intervals. And in this case, you see a lot of wiggles. And that's another thing which is completely obvious, but people tend to forget about it, is that wavelet, at least the Morlet wavelet, which is the standard one. I mean, that's the one you see in paleoclimate papers. The Morlet wavelet is very keen on generating spots. It loves that. And so here, with a process which is completely random, it doesn't have an internal mode, you see many peaks and down and up and downs that you might be tempted to attribute. Look, I have here a cycle at 200 years or whatever. No, it's just the kind of fluctuations that the wavelet likes to do. So basically, what your null hypothesis and experiment with your time series analysis method, this is the key, otherwise you might draw at least non-robust conclusions. So now I would like to introduce you to another time series analysis before we go on with the further with the processes. I thought I would give you a word about it because I think you will get the talk by Sean Lovejoy, and I bet he will say a few words about the Heart Wavelet. So what is it? In fact, the Heart Wavelet, it's a very common thing. And again, if you open textbooks by Percival and Weldon, they speak a lot about it. This is very serious stuff. And the idea of a Heart Wavelet is the following. The Heart Wavelet, it's a signal which has a certain scale and which basically is negative until 0 and positive above 0, and you scale it. So basically what you do is that you try it, for example, with just a time scale of 5 years, 10 years, 100 years, in this case, 500 years. I wanted something big to show you. And you do a convolution between your signal. This is a random signal here. It's a Wiener process for those who want to know, and this Heart Wavelet. And so basically when you multiply your signal by the wavelet, basically what you're effectively doing, think about that, you're doing the difference between two averages over a scale of the length represented by my mouse cursor here. And so when you multiply the signal by the Heart Wavelet, you actually get the difference between averages over a certain scale. I'm going a little bit quick. I realized even by explaining it, it would be so much easier by showing some examples on the blackboard. But what you have to remember is the following. When you have a stationary signal, for example, a white noise, what you may know from statistics is that when you take very long averages, well, the fluctuation of these very long averages is very small, and it gets smaller and smaller as you take longer and longer averages. So basically what it tells you is that the Heart Wavelet variance, I have a LaTeX problem here. The Heart variance decreases with scales when you are in a so-called averaging regimes. So you take a random noise, then the Heart Wavelet will converge to 0 as the scale goes to infinity. In this case, I don't have, you see it, I don't have an averaging regime. I have something which is very non-stationary. It's a Wiener process. And in that case, you have the opposite. It happens that this difference delta will increase as you take longer and longer averages. And so it's a different regime. And this is called, in this case, let's call it the wandering regimes. The Heart variance increases with scale when you're in the wandering regime. So it's a beautiful system because it basically tells you whether you have to think about being in a time scale where everything averages over, so it makes sense to take an average, or if you are in a time scale where it does not make sense to compute an average because the average does not converge. And so one of the, I'd say, creative input of Sean has been to propose a new taxonomy. And rather than speaking of weather and climate, he uses the words, well, still weather and climate, but in a different meaning. But he also introduces the word macro, the macro regime. And his whole point is to say that the macro regime is an averaging regime. And according to him, the centenary time scale is actually a macro regime. It would be the macro weather. And indeed, that's somehow the case. So I take my two-box model in this case. I take the Heart Wavelet variance, and at least for the centenary time scale, I'm indeed, it would be in this case, in a regime when the Heart Wavelet variance decreases with scale. It increases again very modestly here because I don't have a lot of millennial variability in my model, and decreases again. Right, but we don't really believe that things are that simple. I mean, that's everything is linear. Well, maybe they are, but we have to contemplate the option that maybe they are not. So if we take this basic model and think what can happen, how can I modify this picture? Well, what I call the upward integration is basically what I explained so far. So you have noise and it contaminates the whole thing. But maybe I have inputs directly at maybe the decadal or centennial time scale. The sun varies. Well, you read the literature. People like to give a lot of importance to the sun because we get the energy from it. After all, it has some significance. But honestly, it's hard stuff. I mean, maybe there is a cycle at 200 years. Maybe there are other cycles. The problem is that we really need a long, reliable record of over many thousands of years, and it's tough. But we also have intermittent forcing, volcanoes. We know that they start to erupt from time to time, and maybe they have some importance. So I would like to contemplate this part a little bit now. Well, I don't have a record of volcanoes over 10,000 years. Maybe it exists, I have to say. So maybe this is me being lazy. But I wanted to be very conceptual today. So I just took out of my toolbox a model that generates automatically intermittent forcing. And I thank my PhD student, Lilian van der Wecken, to have provided me the code to me. But he's lazy as well, because basically it's a 5-line code. So this is so-called the Pomo-Manville intermittency. And it's an algorithm that rather than generating white noise, it generates this kind of signal. So it's not a scale invariant process. It's not this kind of process that is a fractal. If you zoom it out and out, you don't see the same thing. So there is really a preferential time scale. But, well, okay, it looks like something that maybe could mimic the volcanoes. So if you put that to your toolbox, maybe not. Okay, let's be charitable with me today. So if you put it to your toolbox model, what it does is that basically it excites the fast box, but it talks also to the slow box. And what we will see is that it actually effectively produces a lot of low time scale variability. So this is what happens here. So remember, this is the Heart Wavelet we got with the random forcing. This is the Heart Wavelet we got with intermittent forcing. So it's a completely different shape. I have to admit, I've been overplayed stuff. There is probably way too much forcing. Probably the intermittent signal that has been used here is not the right one. But it's just a kind of easy remembrance that, well, intermittent forcing can actually modify the shape of our spectrum quite a lot if actually it really penetrates into the signal, into the system. Again, I really urge you to redo this kind of experiment with maybe more realistic forcing. Right, we need to move on. So what's the other aspect of centennial variability? Well, then you talk to oceanographers. And if you really talk to a specialist, like for example, our colleague and friend Henk Dijkstra in Utrecht, was worked on ocean dynamics all his life, producing thousands of papers. He tells you that indeed there are modes of motion that can be excited in the ocean and that go from the yearly time scale, like El Nino, a couple of years, to well, maybe 1,000 years. So the ocean can actually be excited on its own. And a very simple way to generate centennial variability is the so-called loop oscillation. And again, I insist this is not my figure. This is redrawn from Hank's figure. They published them in the Pages special issue. And it was reproduced in a review last week. So the idea is the following. Suppose that for some reason, you have a positive salinity anomaly. Well, what happens is that this salinity anomaly, it will play on the density gradient between the low latitudes and the high latitudes. And if you do a little bit of oceanography or physical oceanography, you will learn that this slows down the overturning cell, which is represented by my mouse cursor here. And so you spend time here. So you actually you grow the salinity anomaly. You generate also a heat anomaly. And all of that is being advected to the high latitudes. But what in the high latitude, it's strong because that generates a pressure gradient that actually accelerates the system. And so basically will improve upwelling here and maybe kill your salinity anomaly or maybe get it in the other way around. So basically what you have is the basic ingredient for a loop oscillation. And you can do that with simple model, but the funny thing is that it's also actually being observed in experiments made with general circulation models. So this is a credible mode of centennial variability. Okay, when you're a simple-minded person like me, how do you do centennial variability? Again, you do super simple model. And one of the super simple model you can use is almost the same I've been playing with a couple of slides ago. You remember this one? You got a picture of it. You basically take almost the same equations, but rather than having a fast system which is linear, you have some nonlinear terms, and it's just enough to give you loop oscillation. There are some physics behind it. Basically, what you have is a Fizuk-Nagumo oscillator. The zero here is not a misprint. It's a shame factor I had to introduce because I did all my figures with zero as a mistake, and I have to redraw all of my figures with a one here. But so there is a zero. So it don't scratch your head too much. But I guess the message remains right. So this is basically almost a van der Pol oscillator. So you go with this kind of equation to a mathematician, and what he will do, maybe or she will do, is to produce a stream flow. And the mathematician will explain you that if you look the fast variable across the slow variable, they will basically make a limit cycle. So this is the flow diagram. It's a bit busy, and the red curves are actually simulations with, remember, I have a stochastic forcing here, so it's a bit noisy. So basically, I have a super regular cycle over time. This is the fast variable in this case. Okay, what's funny though is that you have this GT parameter here, and you say, well, maybe the conditions between what's happening at the surface, the fast variable with all its feedbacks, and the slow variable, well, maybe I have some mechanism that make the loop just about to be possible, but not quite. And if it is just about to be possible, basically you have a break, this is this term here, and that makes the system normally not working, not looping, but where a bit of noise can trigger a loop oscillation. And this is what physicists and mathematicians call an excitable system. And it's a very funny system to observe because this is what you would have. So I have now this psi value. So I've got the break, but I'm breaking, but not quite enough to, and sometimes from time to time, I get this excitation. And this is a very plausible mechanism, maybe for Dansgaard-Oeschger events, but that for the next lecture. But why not for centennial variability? After all, what tells you that such a loop should work all the time? I mean, we have sun variability, we have volcano erupting from time to time. So I think that when you're contemplating oscillatory processes like this one, there is a reasonable chance that they're actually much more intermittent than you would like. And they happen, it works, it doesn't work, it worked, etc. And you generate these kind of complex signals that we've seen to start with. So in his review, Henk Dijkstra also explains that there is another mechanism in the literature, and you will see this busy slide because I was lazy again. And just stole the slide from Dijkstra, but I think we stole it more or less from Winton, and then which was reproduced in our oh, I have inspired from a paper in the group of Moji Platif and authored by Martin, and sorry, I forgot his first name. The whole point of it is that this is an oscillation that could take place in the ocean. And the whole point is that it plays now not so much on the gradient, but on the stratification. And we believe that actually some mechanisms, which are called the deep decoupling oscillations, could take place over Dansgaard-Oeschger events. But the speculation is that actually it could also take place as a mechanism taking the Southern Ocean and involving, in this case, the centennial timescale. So I have to crunch here in 10 minutes mechanism that oceanographers contemplate as a possible cause of excitation at the centennial scale. But there are other possible sources. Why not ice sheets? Well, ice sheets, we think, oh, well, these big bodies and they work on time scales of tens of thousands of years, but actually there is a scaling argument, which actually we have just about be making here in a paper, which is it's an ID paper in Earth System Dynamics, which is about to be published. And say, well, actually, you have big ice sheets, you also have small ice sheets, and you have a scaling argument that tells you that they could actually respond with, let's say, damped oscillation. So it's not quite a relaxation oscillation. It's not quite the same idea as the one I've presented. Maybe with time scales of thousands of hundreds of years. So we could have some elements. However, I need to finish the talk because we are already nearing the end on a big caveat. Everything I've been talking about today was for basically understanding centennial variability with a very small number of equations and with basically simple mechanisms. I mean, honestly, this one, it's you know these kind of mechanisms that you can actually express in a conceptual model with a couple of boxes and with heat exchange between a couple of boxes. And it's powerful. You know, if you multiply the boxes, you can have scaling arguments. It's pretty beautiful. However, we still have to imagine the possibility that actually you have some elements of oscillations, or I'll probably say intermittency, which are intrinsically involving a very large number of timescales. People who do turbulence know this very well. I mean, I stole again this picture from a website, but it's a pretty classical picture. It tells you about how turbulence works. You have big vortices, eddies, which break into smaller eddies, which break into smaller eddies. And this is a very powerful mechanism to generate a spectral background which spans many timescales. And can it happen? Can it happen that we have such processes on the centennial timescale? And honestly, I have no idea. I think it's a nice, it's a nice topic of research. When you speak about turbulence, you know what is the object, which is breaking into smaller bits. This is the turbulent eddy. When you work at the centennial timescale, I have no idea of what could be this object which breaks into smaller eddies according to a cascade. I don't know. Maybe the ice sheets can be involved because, you know, especially when you see what's happening at the margin of ice sheets, at the margins of Greenland, at the margins of Antarctica, you have some symmetry breaking processes. But that's a very open-end business. And so far, I really didn't read something that really makes me believe that these cascade processes are at work at a centennial time scale. But I think the possibility is open. And maybe this is something that one of the students who listen to us today will discover in the coming years. It's time to stop, isn't it? So we have our Pages newsletter. Anna produced I mean, it's a bit of teamwork. So I'm speaking about it because I was also part of it. But this review that is just out in Global and Planetary Change. But honestly, if you want to read about centennial variability, there is a huge literature which is not easy to navigate through. And so, well, maybe we should think again about some serious review work that actually would somehow summarize the picture as it is today, because as far as I know, there is no clear big review in centennial variability which is available to the community today. Good. So far, so good. Thank you very much.